Hello to all. Welcome back to the another video of the Synopsys Sentaurus TCAD. In this video, we will learn about the Synopsys Centaurus device simulator and its various transport models. We will discuss the carrier transport models and how it will be used in the MOSFET device simulation. So we have already discussed about the Sentaurus structure editor, Sentaurus mesh, Sentaurus the workbench, all that means we have already designed the Sentaurus using Sentaurus structure editor. We have already designed a device, and now we will simulate and use the different carrier transport model in that MOSFET and out will extract the various outputs. So in this video, we will introduce various carrier transport models, namely drift diffusion model, thermodynamic model, hydrodynamic model, and we will also discuss about the quantum transport that is basically based on the density gradient model. These models are applied in different situations depending upon the requirement of the application. So if we require kind of heat applications, there is a involvement of heat, the involvement of high temperature, involvement of different quantum transport, then we accordingly we will use different types of models. So all the Centaurus device command files are featured in complete workbench of Centaurus project directory. We can easily open the transport model in that workbench directory in the SWB. I hope you will get to know that how to open the SWB and open the transport model. Let's see. Now, when you open the SWB, you can easily see that I have highlighted the example transport model. So you can easily click on that model and it will show on the next window. So we can see that it is already being designed in SWB and it is example. So you can easily use this example to read and to generate the other various files. So see guys, you don't have to write all the files. You can easily extract the files from here as device files, and you can modulate or you can edit those files in the editor according to your device structure. So just you need to design the device in SDE, and from there you have to match the device with the S device file and you can easily run. So do not just learn about SDE, then learn about S device models and all the parameters that are being used in the S device file, and you can easily go to the S visual to extract the various device parameters. So here we have in this project three typical MOSFET device characteristics that we are going to discuss. That is IDVG characteristics, it is basically transfer characteristics, and output characteristics that are being simulated with the different carrier transport models. In addition, the effect of carrier quantization is also being discussed and demonstrated. Now, I have already discussed that how to open the project. You can easily open the project and see in the SWB. Now, MOSFET device simulation with the different carrier transport models. We have already discussed about the MOSFET device simulation how to open the MOSFET device simulation in the SWB. Now, the drift diffusion model basically used, and thermodynamic model and hydrodynamic models are the three models that are generally used in any kind of simulation. But these models are used dependent on your requirement, whether you want to add these or not. So first is your drift diffusion model. which is very basic model for any device. Okay, so we have to add this. So basically it solves the self-consistent Poisson and carrier continuity equations in the designated device region with the specified boundary condition. So we have already heard when you do the modeling, mathematical modeling, you have to specify the boundary conditions. So how do we apply in the simulation? So these Poisson equation with the carrier continuity equations are being used in the drift diffusion model. Now the next is thermodynamic model. Thermodynamic model extends the basically drift diffusion approach to account for the electrothermal effects under the assumption of that the charge carriers are in the thermal equilibrium with the lattice. So here it involves the lattice temperature, heat flow in the equation addition to the Poisson equation and the carrier continuity equation. The third model is hydrodynamic model. It solves the carrier temperature and the heat flow equation in addition to the Poisson and carrier continuity equation. So all these three models are very critical and particular models that we can use in any device simulation. And it also affects the output current as well in the MOSFET device simulation. Now, in the Sentaurus workbench, to activate the particular transport model, we have to introduce the parameter that is T transport that I think you have seen here, IDVG as device in the IDVG as device and quantum confinement parameter. So whenever I have three transport model, which model I want to, if I want to uh, activate drift diffusion model, I will select the node 3. If I want to activate thermodynamic model, I will select the thermodynamic node N4. And if I want to select the hydrodynamic model, I will select the N5. Similarly, if in these three model I want to include the effect of quantum confinement, I have designed the parameter QC and implemented it in the MOSFET and make it such a way that if I want to add the quantum confinement or not, accordingly I will add with my requirement. So it will definitely run the node with the quantum confinement and without the quantum confinement. So drift diffusion transport model is default in Centaurus. Okay, there is no special keyword that is being used in the to activate this model. We can apply the arbitrary device simulations such as MOSFET and BJTs. The typical physics for the MOSFET device simulation with the drift diffusion model is physics Fermi. Fermi basically activates the carrier Fermi statistics, effective intrinsic density, and old slot boom narrow density basically narrow the band gap and with the help of old slot boom model. Now mobility. We all know that any current or any device simulation is not completed without the mobility consideration. So we have to consider the mobility. Now mobility is doping dependent, it is electric field dependent, it is high electric field dependent, hole dependent, electron dependent, e-normal like your boundary condition dependence. Now we will add the recombination where the carrier transports are combination of electrons and holes, where there we have to add the recombination model. So Shockley-Reed Hall model that is also doping dependent and temperature dependent. So all these models are drift diffusion transport models, and it adds automatically when you use drift diffusion transport model that we have already discussed. The last thing is I want to discuss about the drift diffusion model. That equation needs to be solved in the Poisson equation and carrier continuity equation for the electrons and holes. Now these equations are being self-consistently using the couple statement to solve the section. So if you want to solve for the Poisson equation for the drift diffusion, you have to add the statement coupled statement in the solve section. Now, thermodynamic transport model. The thermodynamic transport model required in case considerable self-heating occurs. Most transport model coefficients such as carrier mobility, generation recombination are function of lattice temperature. Therefore, having the correct lattice temperature distribution is necessary to correctly predict the electrical device behavior. To activate this model, must satisfy the you must have thermodynamic in physics section. So physics, thermodynamics, then you can add the different models that you want to add, that recombination, SRH, doping dependent, temperature dependent, all these model you can easily add. Now the heat transport simulation required heat boundary conditions to be specified in the command file, which is done through the thermo mode section, where thermo modes are related to thermoelectrodes, which defined the temperature boundaries condition assigned to them. So we can see, you can easily write thermo mode name, top thermo mode temperature is equal to 300, or substrate or any electrode that there should be at least one electrode that should have temperature is equal to 300 and surface resistance 5 is to -4. The keyword temperature inside the temperature coefficient specify the lattice heat equation being solved self-consistently with the drift diffusion transport equation. As a result, the non-uniformly distribution lattice temperature profile can be seen inside the device. To plot the heat-related quantities, corresponding data sets names must be placed in the section, like temperature, total heat, E joule, H joule, or other things also. Now, next third model is hydrodynamic transport model. See, guys, we are discussing the different models, so we will definitely have to discuss how they work and why we are applying and what kind of result you will get by applying all these models. So the third model is hydrodynamic transport model. Basically, it solves the carrier temperature and lattice equation in addition to Poisson and carrier continuity equations. So it is the combination of carrier temperature, lattice equation, and carrier continuity equation. So this model is specially useful in simulating deep submicron and heterostructure devices. If you are creating any kind of heterostructure device, you have to use this model. It allows non-local effect to included in the simulation, such as velocity overshoot, which can be easily drastically alter the device performance. Now, if you are using you are creating the TFET or the tunnel FET, you have to use the hydrodynamic model. For device breakdown simulation, the use of hydrodynamic transport model avoids the onset of premature breakdown due to the local field assumed in the drift diffusion model. Hydrodynamic carrier transport is used typically for heterostructure device simulation, where the energy transport across the hetero interfaces plays an important role. Now, if you're designing any kind of like silicon germanium interfaces, gallium nitride, optical devices, so there you have to use the hydrodynamic transport models. So be very careful when you are writing the code for this. You can easily get the code for this file. To activate the model, you must specify hydrodynamic keyword in the physics section. Now, similar to the thermodynamic and the carrier drift diffusion mobility dependent models are here in the thermodynamic model, hydrodynamic model as well. Doping dependent, high electric field saturation, carrier temperature derived, and E normal. To solve this, you have to specify like hole, E temperature, H temperature, temperature, which solve the heat equation self-consistently with the carrier transport with the keyword E temperature, H temperature, temperature that should be added by in the set with the coupled in the solve section. If only one carrier you want to add or you want to simulate, then like hydrodynamic E temperature you want to, like electron temperature you want to see, or hole temperature you want to see, you can just specify hydrodynamic E temperature and you can easily specify all other models. It will simulate the MOSFET only for the E temperature model. So the fire carrier temperature drive in the E field saturation statement activates the carrier temperature as a driving force for the electron in the high field saturation model. So you should know that where to what to use. So all these models can effectively use and you can get the result as accordingly your device. If only single carrier energy transport is considered, such as in the previous section, one of the keyword can be omitted, that is hole in this case. And if in addition to deactivate the effect of lattice heating, the lattice heat equation activated with the temperature keyword must not be included in the equation coupled statement. So you can easily like avoid the lattice heat equation not to be solved by not writing the temperature. Now to plot the all these parameters in the plot file, you have to add the temperature, E temperature, H temperature. You can easily get the results after simulating the device. Carrier quantization with the different with density gradient model. Now quantization, we all know that below the 20 nanometer or even below 50 nanometer we have to sometimes calculate the carrier quantization. So how do we add the carrier quantization in this model? So the density gradient model, in addition to the Spondiger carrier quantization model, provides the most physically accurate solution and can be recommended to model of choice to account for the carrier quantization in the transistor channels at the at the hetero interfaces. So if you are using you are creating the device below 20 nanometer, you have to use this carrier quantization density gradient model. The keyword E quantum potential and H quantum potential is activate the density gradient model for electron and holes respectively. If transistor operates under the channel inversion, only quantum correction for minority carriers can be considered to reduce the task complexity. So at a time, it will calculate the quantum quantization only for one carrier like electrons or holes. You must include the E quantum potential in the keyword in the coupled statement to calculate the various Poisson equations, Spondiger equations, and various self-consistent equations in along with the other models. So if you want to plot the potential E quantum potential, you have to word the E quantum potential in the plot section as well. So how to get the output from the MOSFET device simulation? Now IDVG transfer characteristics is the first MOSFET device characteristic simulated in the application project files. In this file, the model selector select. Now we have to know there is a file that I want to show you that how it looks. So this is how it looks. So there is a model selector file. There is a quantum correction section. There is a field section from where you can easily get the various files. Electrode section, thermo modes section where you are giving the different types of temperature and surface resistance to the different electrodes. physics sections where you are adding the different models, quantum models, Fermi, and accordingly you are adding the different dependent models on those. Now next is plot section where you are plotting the different types of models and their output characteristics. And last is math section, and the least is solve section. So all these models are being used in this file. So if you want to select the uh, diffusion model, you have the file will select the diffusion model using the T model. If you want to thermodynamic, using thermodynamics, I have already discussed that how it will use the thermodynamics. So see here you can easily select the various models. So I have already diffusion, thermo no, thermo yes, yes, no. So in this respect you can easily get to add the various transport models. So after that you have to give the various biasing condition, initial bias and gate bias condition using the Sentaurus workbench. So VDD and VG initial is -1 volt and 1.1 volt for supply voltage. For simulation with thermodynamic and hydrothermodynamic, at least one thermal contact must be specified in the thermal section where the thermal boundary should be defined. So that we are defined in the substrate section. So in the solve section we have already discussed it about in the previous, that how to add the various uh, uh, keywords to solve the section. So here we have two biasing conditions, that one we are sweeping the drain biasing and second we are sweeping the gate voltage biasing. So accordingly we will get the result. The current plot statement ensures that it is basically you can see that electron density with the quantum confinement effect and quantum confinement with not including the quantum confinement effect. So with confinement effect you can see that the effect is very accurate, and without quantum confinement effect the effect is that not that much accurate in the polysilicon and the silicon as well. So the carrier distribution across the channel with and without quantization has been we have discussed. Now we are discussing the IDVG characteristics, that we know that with the consideration this shows the hydrodynamic model blue line, black line shows the drift diffusion model, and thermodynamic model shows the red line. So we can see that with the accuracy with quantum confinement effect accuracy is more, and without quantum confinement effect accuracy is little bit less. So we have to use the accurate model and we can use easily in it. Now that how to see the temperature, you just all these parameters you can easily use in the S visual. You just need to open the file and open the S visual and your TDR file in that visual. So your temperature after thermodynamic model simulation is seen like that. Your lattice temperature you can see in the figure. Now E temperature you can also see in the figure. Okay, left is your lattice temperature, right one is your electron temperature distribution in the MOSFET at various VGS and VDS voltage. So all all the MOSFET simulations that you have want to use, you have to add all these models. So I want to end this video with the note that if you're designing any kind of device, you must have the knowledge of various different models, why we are using those, and how we can easily apply in our device structure. So for this, thank you so much. I will come up with another video in the next week. Thank you so much.